Rains, people make it.
Yeah, but today's cold.
Is it cold?
It is cold.
It is. So, who has ever conducted a machine learning experiment? You did. Today, like, I'm just gonna spend, I don't know, maybe like half an hour on introducing this, and I think it's interesting because this is very important. Some of the others will figure that out. Also, as I mentioned a week ago, we're gonna have like a quiz next Wednesday. So we'll need to prepare that. And also we're gonna post a homework this week, I think, about running a machine learning experiment. And I want to see everybody present the results and experiments the right way. So we're just basically going through a couple of options that we have and a couple of like things that we need to talk about with machine learning experiments, just so that we do not report wrong results or don't like underestimate the generalization error and so on. And yeah, so this is just basically the basics of a machine learning experiment. Okay, so first we have training, validation, and test sets. Every single time you start an experiment, you will have a test set, or like a data set that you will work on. So most of the time, these data sets are like interesting to a problem that you have. You might have collected that data yourself. You might have started to participate in a challenge. There it is really hard to actually make a mistake. But oftentimes you just have like collected your own data and you have like from start to end all of this data. But you shouldn't like use the entirety of that data set for training or validation or testing. So really what you need to do is split it up in these three sets. So first, the training set is going to be the largest set. So like often if you have a data set, you would use something up to like 80% of the data for training, or 75% of the data for training, and the rest you would split up in validation and test. Okay? So in the training set, you use that to construct and train your classifiers. And so for example, you would use that to like find thresholds of your rectangles, or you would find the separation hyperplane on this set, okay? And the second one is the validation set. With this validation set, you identify which algorithm or which machine learning algorithm or which hypothesis space, rectangles, linear separation with a line, neural networks, etc., which one works best on my data, and what should be the parameters, like the hyperparameters, how to like construct that algorithm. And in support vector machines, or so like you would first choose your hypothesis space, neural networks, support vector machines, decision trees, etc. And we're going to talk about all of these. But that's like choosing the hypothesis space. The second one is like choosing or like finding out which ones are the optimal hyperparameters. So like the number of layers in my neural network, the size of the layers in the neural network, the kernel function in a support vector machine. Is it linear? Is it a polynomial? Is it a RBF kernel? And so on. So you have to choose those hyperparameters with this validation set. Okay? And once you have found your best performance on a validation set, then you approach the test set. Okay? So only after you have validated which are the best parameters, you're going to use like run this on the test set. And the test set is really there to estimate future error and generalization capabilities. Okay? So that one's the one that you need to report the most. Okay? So that's is the most important to be reported about. But it's never used for optimization of performance. And we never only report the best run. And we'll see what I mean with this. But basically, training, validation, and testing can be done in multiple times. So you can always use different 75%, for example, for training, different 15% for validation, and different 10% for testing. You can rotate that through. But you would always conduct the entire experiment once, and then set it in stone and repeat the experiment. So you're not reporting just the best run ever, okay? So that's important. So let's visualize this a little bit. So we have our labeled data that comes in. We split it up in training, validation, and test sets. And these sets are all mutually exclusive. And a lot of these slides kind of say the same thing over and over again, but it's kind of important. Then we conduct training and validation, which is basically we estimate the parameters on the training set. So this is kind of like finding the right thresholds, finding the right connection weights in a neural network. We use the validation set to tune our hyperparameters, so number of layers and so on. And then we evaluate. And we're going to talk a little bit about this, but there are many different metrics that are possible. We need to choose accordingly, so we cannot just choose one and decide that that's the best one, even though it doesn't really fit the data, and you'll see what I mean with that. And we report results on the test set. And really, if we do not do this, we are over optimistic about what we're doing. Okay, so for example, if you just run this and report on the validation set only, you would only then report after you found the optimal hyperparameters, but you have optimized on that data set already, right? So you don't really know how well your algorithm would do if it gets to use or gets to see data that it has never seen before, right? So you need to keep that in mind. And yeah, a lot of people make this mistake and would just report in the validation set, which is kind of a problem. So if you're participating in a data challenge, for example, you'll only get access to the test set at the very end. So what you would also do is you would also report your validation results. But then you would send in your results on the test set to the challenge organizers, and you would get like a metric back. So you often just see both the validation set metric and the test set metric. But what we're really out for, what we're really interested in, is like how you're performing on the test set. Then some statistical thoughts or issues. So in general, we want a classifier which does well on the test set. And we need to make sure that we are kind of like not, so like overfitting is a problem sometimes, but what we need to do is we need to like attempt to not like be perfect on the training set. So it's like if you build the most complicated classifier, you can always like overachieve on the training set, but what we're really out for is the test set, and that's why we really need to keep that test set separate. Okay, so overfitting can become a problem if you're too focused on like improving your test training performance. Okay, and to get a better estimate of like what the performance really is, we kind of also like want to rerun these experiments multiple times. So you don't just want to test in one run, okay? And so this kind of is mainly the process that you have to engage in to come up with a good algorithm and a good report about that. Does that make sense? Most of it? Okay, good. So I brought also like a couple of extra or special considerations. And this is only an example for that. So like you cannot just, so if you have your data set, you get this entire like big file or whatever, and every line is one data point, for example, or it might be a sequence of data points in one line, right? You cannot just go ahead and randomize that order and take out 75% and use that for training and use the other 15% for validation and 10% for testing. But you need to also think about like what is in the data. So for example, we deal a lot of times with data that is from individuals, like a video that are recorded about like from a person, right? Or it might be speech that I recorded from an individual. So if I then scramble all my data points, I can make a lot of mistakes. So for example, I could have my machine learning algorithm learn the hidden variables of like how my voice sounds like, rather than how my behavior generalizes to other people. So it would overfit on a person. So what you need to do in these cases is you go ahead and like identify which lines are representing one individual. So that's kind of like a super like category of your data points. So all of the first 150 lines are one individual. What you need to do now is you need to make sure that all of these 150 lines go either into training, validation, or test. They cannot be mixed up, okay? That kind of should make sense that way. So you don't want to like learn something that is not representative of what you want to do. So for example, if we do emotion classification, right? We have data recorded in 5 different emotions, so we have multiple recordings of each different emotion, but we have only 10 people, right? And if I go ahead and say, I mix that up and I want to now classify if that emotion is happy or sad, I might actually have learned how this specific person sounds like when they're happy or sad, and when like how they sound like when they're angry, right? And so like you just want to make sure that you're not falling into that trap. Okay? Very good. Sometimes, however, you also have to think about that, like there might be exceptions. Sometimes you actually, for example, you like follow a person with a mobile phone, you record their daily life over like a year. You want to identify if they're maybe getting better or getting less depressed or like working out more. And you only have sensor data, right? So you might want to then keep the data for one person inside your training set and validate or test on the same person's data. Okay, so there are special considerations about that. Okay. And I would like to illustrate maybe one example that I've seen at a pretty well-known conference. It's an ACM conference that I went to in 2015, and the idea of the paper was that they use like an inertia sensor, like a wristband, on both hands, and want to identify when the person's eating. Okay, so what they would have is like data like this. It looks like that, so that's like from the inertia sensor, person's eating now. Okay. Sometimes you would have like something like this, or like some noise in there. The person is not eating here. Okay. So what they did, they recorded these individuals for hours at a time, and then they had a person or multiple people and look at the data and say, okay, I see on the video the person's eating from here to here, right? And each of those points here is actually, like, this is not like a continuous line, this is sampled at like maybe 10 hertz or 20 hertz or something like that. So this is sampled at 20 hertz. And what the paper talked about was that they did a 10-fold cross-validation, and their classification accuracy on detecting like if the person's eating or not was 99% correct. And I'm like, wow, I don't believe it, right? Paper got accepted, like paper was presented, and everybody was like, oh yeah, this is really good, like I really need that, I want that, but honestly it didn't work, right? So what is the problem if you just do 10-fold cross-validation? And you might have heard about that. So tenfold cross-validation is the following. You have a training set, or you have a data set, and you take out a tenth of the data, and you use that for validation or testing, right? And the other 90% go into my data set for training, okay? So that means, and in their case, it was interesting because what they did is they cut out windows like 5 or 6 data points in one window and decided for every 10th of these windows, or at a random pace, but about 10%, if it goes into the training or the test set, right? So, so they had like these windows, and it could even be worse. The windows could be overlapping too, right? Sliding windows could be there. And for each of them, they said training or testing, right? And most of them were training, testing, whatever, like let's call testing E, makes it easier, faster. And we did, again, training and so on, right? Okay. You already see what the problem is, right?
So the learner saw all the data, more or less all the data.
The machine learning algorithm saw all the data,
Yeah.
right? It saw like this data point and its immediate neighbor. And it might actually, as I said, it might be overlapping, right? It might be almost exactly the same data except for like 1 or 2 data points that are outside. So if you just do a nearest neighbor classifier that tries to find the closest neighbor, you would almost always find the correct answer, okay? So it's very important not to make these mistakes. So what would they have to do? Like, what would be the ideal thing? They have this for like 5 hours, 5 hours of data annotated and so on, and they have 30 individuals. So what would they have to do?
There's a couple of problems that they're going to happen. They will have a hugely unbalanced set, which is what happened to us because you don't need the whole day.
Yes.
So working with unbalanced sets is a huge problem.
Okay, let's
So
ignore
that's
the imbalance for now. We're going to get to that
they
in a
have
second.
30 people, and mostly this is definitely a European study, because Americans eat with their left hand on their lap. So 2 would not make sense. Totally,
You might engage in the act of cutting.
What? Right? So that doesn't happen. So first, they probably haven't checked all the 5 hours to label it. They probably did some pre-selection. Most likely.
Okay, but
this one. Let's say they did. They have 30 people. They will have their idiosyncratic movements.
Yeah.
So it will be so much smarter. First, they will probably have to use something that is time sensitive like HMMs, because then they will be able to track this. The other one is use it per person, figure out per person, and leave training people outside of it. And they will have a completely different...
That's what I was
It's a
looking for.
completely
So
different strategy.
You would do 20 individuals for training, 10 for validation, and 5 for validation, and 5 for testing, right? So that's what they would have had to do, okay? And then the results will be like, I don't know,
60%
30%
if they're lucky.
correct.
Yeah.
If they're lucky. No. Yeah, so 60% if they're lucky, 75% if they're lucky, okay? So that like kind of needs to make sense, because this is really like one mistake that I've seen so many times, and I'm really tired of it. Like that becomes.
But you know what is fantastic? That papers like this get accepted.
Yeah.
So
Indeed,
there's chance for us.
Right, and so I mean I can tell you another story about this. So I can tell you another story about this, which basically goes in the direction of, okay, so we collect our own data, we try to identify if a person has depression or no depression, and we do that in the right way, like we keep out people for the testing and so on, and we get about, I don't know, 75, maybe sometimes 80% accuracy, right? And then I get a review back and it says, well, but it looks like you're a lot worse than what the other people did, which is 95% correct. And I'm like, okay, so now I have to justify why my experiment that is the one that's the only one of them that is correct has a lower performance than the ones that got accepted. So this is really like, I mean, at some point, I guess, we have to overcome our dependence on performance a little bit. So just to make that more clear. That, yeah, so there's a lot that hinges on this. We really need to be careful about what we publish and what we work on. Because in the end, like it might bite us anyways, because you have to justify your performance, and often you want to improve on something, but if improvement cannot be attained because there was a mistake in the experiment. So like one of the things I do in my reviews right now all the time is I check right away the performance and the experiment, how it was conducted. If it was not properly conducted, it like gets a very red flag.
It
and it's
make
sad
sense.
sometimes because I think methods are new and interesting, but if you don't evaluate them properly, we will never learn what they actually are capable of. And so yeah.
But by introducing data that is used for testing, it becomes a search.
Yeah.
Because you have it, you just have to find it.
Yeah.
And then 99 is actually not a grade, it should be
No, it
99.9,
actually should be 100, yeah.
right?
Yeah.
Because you're finding it.
Yeah. Okay, so that's a little rant here. There is a couple of other methods or considerations that might make sense sometimes that I would also like to mention. So for example, leave one out is a special case where you kind of like leave a single data point out for testing. This has been done a lot in the past when you have like very, very tiny data sets. So you don't have a lot of data, and it might be really, really expensive to get data. So for example, it might be very expensive for you to get X-ray images for patients with a certain illness or something like that. So you only have worldwide maybe 15 cases, and that's all you have, right? So it might be a problem there. If you have, like let's say, 15 individuals and you want to do the spoon, like the eating detection, you could run an experiment and say like leave one individual out. So that's a special case, like leave one subject out or leave one like data sequence out. Okay. Pros, well, you learn a really good classifier actually, and they are quite robust and accurate. However, again, you're using a lot of the data, and you have to repeat the experiment n times. So, like, because you need to make sure that every data point was once used in testing. So, if you have 30 individuals and you want to leave one individual out experiments, you run this experiment 30 times. Okay, at least. And so that can become quite expensive to do. Yeah, and the observations and training test set are not balanced, obviously, because you only have like one point in there. And it becomes very difficult to use some of the metrics out of the box, so you would have to like collect the data first and then run the experiments. Okay? All right. Questions for that? All right, so we can now like continue to some evaluation measures, and this is also very important. Like as Natasha was starting to talk about, like imbalanced data sets, and there might be some issues there. So we really want to identify like how well is our system doing, like how accurate is it, and how performant is it. Okay, and sometimes a lot of different metrics can be used. So for example, if you're not so much interested in like how accurate or how well your system recognizes certain patterns, you might be more interested in like how fast it is. So you would report on like the speed or the learning time and so on. That is a valid metric for some experiments. But often you're interested in like how accurately your system classifies a certain pattern. and the number one go-to metric for everybody all the time is accuracy. So I have a class A and a class B. I want to know how accurately I classify class A and how accurately I classify class B. So I can produce like an accuracy of like 80% correct, okay? But this 80% correct often alone doesn't make a lot of sense, and I would like to show an example here that is showing this. So we have a data set that's incredibly imbalanced. We have way more red points than blue points. And if we want to classify, for example, using this line here, we make a smaller error on accuracy than if we classify with this line here, right? So this one would actually give a better accuracy than that one. But my task might be identify the needle in a haystack, right? And if I get the two needles in the haystack and maybe have like 4 not needles, and I might actually be way more interested in the blue class than in the red class, then actually the A classifier is a lot better than B, okay? And this kind of makes a whole world of difference, and often you deal with these kind of imbalanced classifiers, or imbalanced data problems, okay? So where most of the data is background, but you only are looking for like a few items that are important. So for example, also in impression, for example, when we have our data set, we have 700 individuals recorded, and out of those 700, I think maybe 20% are depressed. If I report 80% correct, that doesn't mean a lot, because I just might say, no, they're not depressed on every single individual, right? So that's pointless.
We had that.
Yeah.
We had 7% was positive,
Right.
So classifier very quickly learned to
Always say no.
shift to just some zeros.
Yeah.
And it was 93%
Exactly.
accurate.
Yeah. So that's why we need to like further investigate and like come up with different metrics. Okay. So again, which one's preferable? As I said, depends on the task. If you want to classify reds, well, B is fine. But if you want to identify the blue ones. And a way to immediately see that one class is overtaking everything and like your classifier always produces one side of the coin is if you also provide a confusion matrix. The confusion matrix in the two-class problem is visualized here. So this is the actual target. So you have positive and negative. And then this is the outcome, the test outcome, positive and negative. So this works like this. So you have a data point that goes into your classifier and has a label, it's 1 or 0, right? That's the ground truth, so you would choose in this column or in that column. And then your classifier says 1 or 0 as the output, and then you would choose which row, 1 or 0, okay? And if the ground truth and the outcome are the same, you would count here 1, so that's true positive, and if they're different, you would count either a type 2 error, which is false negative, or a type 1 error, which is a false positive. So false positive error is like a false alarm. Your classifier says wrongly yes if it should say no, and a false negative is your a misclassification, or like a miss in detecting. Which is basically your classifier says no if it should have said yes, okay? So that kind of makes it clear, and in particular in medical studies or medical investigations, these two different types of error have very different costs, okay? So if you're saying to a person your test outcome is positive, if they don't have the illness, a further test might confirm that they don't, so that the cost is the further test. But if you say, no, you don't have the illness, the further cost might be their life or some other other thing that might happen to them. So it's very different costs, and you can balance this out. So sometimes your classifier you might are more interested in reducing type 1 errors or type 2 errors, and so you kind of want to like gauge in your validation which error is more preferable for your case. And so this is kind of like a visualization as a Venn diagram. These are like the rectangles, all instances that are that can happen. So this is kind of like the input space. All the true negatives are out here in this soup. The false positives are when your classifier says it's positive, but it's like it actually is not. The true positives are in here, and the false negatives are the positive instances that your classifier says no to. Okay. So this is kind of like a visualization. And so now we can come up with metrics using these true positive, false positives, true negative terms. So these Tn, Fn, Tp, and Fp, which are in here, we can now come up with metrics. So we can use this to define classification error. So that's the number of errors divided by the total number of items that I have. Accuracy is the total true divided by the total number of cases that I have. Okay, and so this is very hard and like not a really good measure for detecting if the world is ending already, or like that will only happen once, or earthquakes are pretty rare. So these are not necessarily the right way to go for a certain number of problems. Okay. So we can come up with other metrics. And so, for example, the false alarm rate is interesting. So that's the false positives divided by the false positives plus the true negatives. Okay. I can come up with a miss rate, false negatives divided by true positives plus false negatives. Okay, so you can see you can come up with all these different kinds of metrics, and the recall is very important. So this is basically the number of positives we classified correctly. So out of all the positive samples in the data set, how many did I find again? Okay, and then the next one is also important, which is the precision. So out of the ones that I classified as positive, how many were actually positive? Okay, so this one's true positives divided by true positives plus false negatives. This one's true positives divided by true positives plus false positives. Okay. So these two are very important and happen a lot. Like what's also very important is you never want to just report one of the two. They make no sense alone. Okay, they always have to come in pairs. So you can report these two, or you can report these two. All right. So does that make sense? So for example, if I only report recall, I can say I have 100% recall, but that just could mean that my classifier always said yes. I also need to report how many times it said positive or true when they were actually positive. Okay, so that's important. And you want them both to be close to 1 or close to 100%. Okay, so always report in pairs. And now we can also move a step further and say, well, I can also assign costs and utilities to what my mistakes are. So for example, I can create a cost function that has the cost for true or false positives and the cost for false negatives. And you can choose a different value for these C parameters here. So the cost could be different for a different type of error. Okay? And there are many different types of cost functions, and a lot of times cost function is really the one thing that you use or that you need to update to improve your algorithm. And then the second one here, which is one of my favorite measures, is the F1 measure, which both like weights recall and precision the same way. Okay, so it is equally important for this measure to have a good recall as well as a good precision. So that's the harmonic mean of precision and recall. Okay? So that's a cool measure, and like often report that measure plus some standard deviation, etc. For the measures as as the performance. So in most of our depression experiments, we would report accuracy, F1, precision, and recall. Okay? Alright, so let's summarize this. In like what do we do for reporting machine learning experiments? And so we only report performance metrics that were achieved on a test set and, as I said, occasionally on the validation set only. Like we don't care about training accuracy, like that could be 100 all the time, doesn't matter. And we need to choose meaningful metrics, so like don't choose accuracy if accuracy doesn't mean anything for the experiment. And we need to report a baseline metric. And the baseline metric could be as simple as the prevalence of like a certain class in my data set. So in my depression experiments, if I always say no, the person not depressed, my baseline could be 80% correct, right? But the F1 measure for depression, for example, would be terrible. It would be abysmal. It's like non-existent. You can't even compute it because you divide by 0. And so you could have a baseline metric that says 80% of the time it says positive or it says negative. So you report 80% correct as a baseline metric. Or what happens, for example, if you randomly choose a class? If you have a balanced classifier, a problem where like 50-50 are positive and negative examples, you randomly choose to say positive or negative. That would be like the performance metric. Or you could choose based off of the prevalence of a certain class to like select randomly between the two, like positive and negative. So think about a baseline metric. And the baseline metric could also be a simple classifier, like a k-means, like a nearest neighbor classifier, or I don't know, a simple naive Bayes or something like that. Okay, so think about baselines. And then we don't just report the best result, but both the mean performance and the variance of the performances. So we would report the F1 measure that we got, but also the average of the multiple runs and then the standard deviation of that F1 measure. The exception here, obviously, again, is if you run in a challenge and you always have the same test sets, you would always like have that separately. You don't report mean performance because obviously like you only have one run. And if you want to claim statistically significant improvements over a baseline or another classifier, I would like to see statistical tests. Often you just see, oh, we're like 3% better, but we don't know if that means anything. If like the next time you would run, you would be 3% worse than the previous one, and so on. So that makes a difference. And then like I also like to see some interpretation of the results, like what mistakes were made. Did I make type 1, type 2 errors? What can I learn from those mistakes, right? And I would like to see some visualization of the results, like maybe a box plot. Hey, this is the average performance for the baseline. This is the average performance for us now. Like we make a lot less errors, so we want like just to visualize what's happening. And then confusion matrix are really nice to see what's going on. Okay, so that's kind of that. I have a few examples that I might want to show. So, as I mentioned, in some of my experiments, we would report accuracy and then the F1 measure for the positive and the negative class. So that's one way to do that. That's also that's in leave one speaker out testing, so like the subject was always removed from the test, from the training. Then sometimes we report results like this, where we would have a baseline, another baseline, and the method that we want to propose, and you see like different errors, and you have these stars again. Hey, the stars means like we statistically outperform this one like highly significantly, and this one significantly, in a cross-validation experiment. And in this case, we actually made that mistake of like throwing data from one person into both training, validation, and test. Okay, but then we also report this. Okay, so we just wanted to see what's the difference, and we can see that the difference is really low actually. So our model learns something about the behavior rather than the individual. The individual helps, but it's robust if you leave speakers out as well. Okay, so you can do this, but you can also you then also have to report something else. Okay, and then another thing that we did in this same experiment was that we also plot the confusion matrices for leave one out and cross validation, and you can see like the confusion matrix is not reduced always to like just two classes. It can be any number of classes that you experiment with, and then it also allows you to further investigate what's going on, right? So what we can see, and I don't know if, did I show this, like breathy, modal, tense? So breathy is like breathy voices, modal is normal voice, and then tense voices, okay? And so you would think, okay, it's important, like it's unlikely that I'm gonna mistake a breathy voice with a tense voice, right? They sound very different. So I don't make this mistake with breathy and tense, or breathy and tense here. I don't make this mistake often, but I make this mistake more often, which means that the modal class is really like causing the errors, okay, because it bleeds into one side or the other. And in this case, if it's speaker independent, it might be because a person's modal voice might be more tense or more breathy, depending on the person. Okay, so you can learn a lot from these type of like visualizations. All right. So that's mostly that, and I think we can do a 10-minute break, and then Fishing will start the scikit-learn tutorial.
Cool.
Right. So yeah, 10:55. I think I'll probably sneak out after the break because I have like institutional review next week, and I need to prepare for that.